See if I can get this all started properly. Do the incantation. So, last time we sort of finished off, remember, explicit allocators. I have an allocator, but it expects me to tell it when I'm finished with memory. And hey, guess what? People aren't great at doing that. But we talked about it nonetheless. We talked about a few interesting issues as far as being able to access before the beginning or after the end of arrays, which is always full of excitement and fun. You can have programs that do things completely different than what you intended them to do. But we have gotten through just about all of C that we're going to talk about. There's a few more abstractions. There's like one more abstraction we're going to talk about this week. And then when we get into threading, you'll see that you could actually implement that in C and assembly as well. But for now, we've basically covered everything in C that we really care about. And as I say here, we started to notice that we can write programs that are really easy to break and without intending it at all. You can, for example, put a buffer on the stack, and if you're not careful about accessing it, you can easily have a program that can then be compromised and used to do things that the program wasn't intended to do. And that tends to happen a lot. Does anybody follow like computer security bulletins or anything like that, just as a hobby? Okay. So if you become a system administrator ever, do that, because if you don't, you're going to have sad users. But you have a server running on the computer, and people are accessing it. And if you can figure out how to get that server to do something that you didn't intend it to, then you can now compromise that system. And so we started to look at a few of those kinds of issues. Unchecked array accesses, buffer overflows. That was really annoying. And then, of course, we have all the more run-of-the-mill memory management issues. Seg faults, which always makes us happy. Memory that we don't deallocate. And if you have a program running for a long time, it runs out of memory and then fails. And, of course, another one that you could mention up here is actually fragmentation, because if we deal with memory management properly, we can actually solve the issue of fragmentation as well. Okay. So what language designers say is, why are we giving people all this power? Why hand people a shotgun when all they need is a pointy stick? Something like that. So if we have people that aren't writing programs that actually need to be able to do pointer arithmetic or low-level hardware manipulation, don't actually expose those facilities at all. Let's provide a simplified system that allows people to write correct programs more easily. And so we started talking about this at the end of last lecture. How would we actually present these things as abstractions? And so again, we're taking another step up the hierarchy of abstractions. We will have greater capabilities in some areas, representing types, type hierarchies, for example, but we'll also limit what we're able to do at the lower level. And so hopefully that'll allow us to have fewer security holes. The other thing that you notice in these runtime languages is that, or these higher level languages, is that the runtime grows. The Java runtime is huge compared to the C runtime. C runtime is like the allocator. That's it. C++ runtime is the allocator plus some exception stuff, plus a little bit more. The Java runtime is huge compared to those things. And it's true of other languages as well, higher level languages. And they do tend to be slower. Now, that's not entirely the case anymore, which is really kind of another really cool topic that I would love to spend some time talking about, but we just don't have time for it, which is the ability to just-in-time compile these higher level languages code into something that's actually native. And again, if the interpreter or the virtual machine does this, it can actually achieve performance that is on par with C and C++ programs, as long as it's something that C and C++ aren't particularly good at. Like if you have a Java program doing a whole bunch of number computation or parsing data buffers, it can actually approach C and C++ performance very easily. I've done it. I'm sure all of you could do it too. But if you have a Java program that's manipulating memory, allocating and deallocating objects, you will find that it is way slower in general than a C program doing that, because C is just better at that stuff. It's got way less overhead for that kind of stuff. So these were the language features. I'm not going to spend too much time talking about this, but these are the things that we're going to go through in the next 3 lectures. So today we're going to talk about implicit allocators and garbage collection, and then you'll see what we talk about on Wednesday and Friday. And we're going to look at how we could actually map these down to C and assembly language. And it's kind of exciting to me because a lot of people don't actually understand this stuff. If you get on Reddit or you get on any sort of programming discussion forum, or if you go work at a company, A lot of people don't actually understand these things in very great detail, so it's very exciting to me to be able to talk about them. We will look at Java-like languages. So you can imagine Java or C++. There's a lot of similarity here. Obviously, C++ doesn't have garbage collection. You could think Python, that kind of stuff. So we'll be talking about some of these features, how we would actually implement them. Okay, yeah, so explicit heap allocators. Remember we said the program has to say when it's done with memory, but programs are not great at this. I took the politically correct program term as opposed to saying programmers are not good at doing this, but really it's our fault. we are all to blame here. So what we do with implicit allocation is we allow the program to focus only on when it needs memory, and then the allocator itself figures out when memory is no longer needed. And so we have this process called garbage collection. You can imagine the program is using memory, and then it decides I no longer need this memory, and now that's garbage. You know, we have a very descriptive terms in garbage collection, actually, it turns out. And the allocator goes through and hunts and says, oh, you're not using this memory anymore. I'm collecting the garbage. I'm going to take that back, and now when you ask for more memory, I will be able to give you another chunk of memory from something that I've reclaimed. And it does eliminate a lot of issues. There is overhead from doing garbage collection, and that does have an impact. It used to be much worse than it is now. Like I would use a text editor written in Java, and every once in a while it would run out of memory and do garbage collection, and it would be like 30 seconds while I'm sitting there twiddling my thumbs waiting for the editor to come back so that I could start typing again. We don't really have that issue anymore. They're much more efficient at doing it. We'll talk about a few of the things that they've done to improve it. But it does make things a lot better. Typically, the way garbage collection is done is it figures out this thing called a reachability graph, which is just a fancy way of saying, what stuff can I still reach from starting points that everybody sort of agrees on? Like I have a local variable that's a pointer, and it's pointing to a chunk of memory. Well, that variable is a starting point. We call it a root, or we call it an anchor. And so that's one anchor point in the reachability graph. What can I now reach from that starting point? So variables on the stack, do I have global variables that I can reach things from? And if I can sort of figure out what this reachability graph is, then I can tell what parts of the memory are not accessible. And those things are therefore garbage. Okay? So like I say here, some allocated nodes are root nodes, so global environment, global variables, or on the stack, so local variables or arguments. And anything that's reachable from these roots is, we call it live, so it's not garbage. So you can see that we have 4 objects over here that are garbage, and these things need to be identified and then reclaimed by our allocator. So yeah, the obvious question is, how do we determine this reachability graph? Now let's say that we were trying to add garbage collection to C, or we're trying to add garbage collection to C++. Is it possible? I said that there is a C and C++ garbage collector last time, so yes, it is possible. It's just really hard. And the reason why is there's actually a number of reasons why. The primary issue is that you can have values that look like pointers. You're allowed to do pointer arithmetic, so it's hard to identify what things are pointers. You may have some crazy code that takes a pointer and casts it into an int. And now it's an int and you don't know it's a pointer. And then later on, somebody else casts it back to a pointer, and you use it as a pointer, and it's like, oh boy, how does a garbage collector actually deal with all of these things? So yeah, pointers into the middle of memory blocks, pointers into the middle of structs and arrays, casting pointers into pointers of other types or non-pointer types, also an option. And then, of course, pointer arithmetic. So because we have this situation, it is hard to identify what things are actually pointers to other things in C and C++. Okay? So that makes it hard, but we can still make some assumptions and try to crack this problem. What garbage collectors in these languages tend to do is say, if it looks like a pointer, I am going to assume that it's a pointer. And how does it tell what looks like a pointer? Well, if it is a value that could reference a valid portion of memory in the program's current address space, then let's assume that it is a pointer, because that's the safest thing to do. Okay? Now, how do we know what memory is currently valid? I showed you that picture of how processes are laid out, and we had the stack at the top, and above the stack was the kernel, and below that somewhere is the heap, and there's this big empty space in between. And then we have uninitialized data and initialized data and program code. So we have specific areas of memory that we know are occupied by things. And so we can look at these values and say, well, does this value, if I treated it as an address, does it actually reference one of these valid areas? And if it does, we'll say, okay, I'm going to pretend this is a pointer. I don't know for sure, but I'm going to pretend. Okay? So what happens if the value isn't actually a pointer? What is going to be the consequence in our determination of the reachability graph and our collection of garbage? What is the worst thing that's going to happen here? Run out of space. Let's not be so fatalistic. That may in fact happen, but let's like, what's a more basic consequence of this? Yeah, that's really, and that would be the thing that would lead us to running out of space. But the major issue that we have here is that if it looks like a pointer and is a pointer, we'll be fine. And if it looks like a pointer and it isn't a pointer, we may think something is reachable when it's actually garbage. So that's okay, right? Because we're not freeing something that a program thinks it's actually needing. Right? As long as we don't free anything that is definitely not garbage, we're okay. And so, like I say here, the only drawback is that the garbage collector thinks some memory may be in use when it isn't. And hopefully this won't happen very often. But we call this garbage collection strategy conservative GC because it is conservative about what it releases. And like I say here, all reachable blocks are identified, so that's fine. We won't cause problems for the program. Some unreachable blocks may still be identified as reachable. And so the consequence is that we may not release all of our garbage. If we can live with that, if we can suffer through this conservative garbage collection and not run out of memory most of the time, then we're okay with that. We can deal with this. Now another approach, which is the approach that most of our higher level languages actually take, is to basically get rid of the idea of pointers. We're going to replace pointers with a more abstract notion called a reference. And we will not allow people to do the crazy stuff that people do with pointers in programs. Okay? Get rid of pointer arithmetic. We have real strict constraints on pointer casting. We don't allow casting to a non-pointer type. And if we do this, then we can actually have precise garbage collection where we are able to determine this reachability graph precisely. We can free all of the unreachable stuff, and we can free none of the reachable stuff. So we're actually able to do this precisely. And like I say here, given that in C you can have an array and say, let's say it's called A, an array A, and you can say array A minus 5, index minus 5, set it to something. C allows that. So maybe I should actually take away that ability in the first place, because then it'll lead to better programs. Okay, I don't want to take a pointer P and be able to add 300 to it, and suddenly I'm in la-la land and I trample something else or I cause my program to crash. So who started working on the allocator for assignment 3? Who has had their allocator crash? Who has had their allocator corrupt the actual memory heap? Yeah, so see, these are the kind of things like, whoa, wouldn't it be nice to have a world where that can't happen? We disallow it. Okay? Now you can see that writing an allocator, you have to be able to do this stuff, but let somebody deal with that, and then all the unwashed masses can go ahead and take care of writing programs that don't have to think about that kind of thing. So Java has references, Python has references, a lot of languages have references, and references are just a way of identifying an object. And you can think of pointers as being a really primitive version of a reference. It just has the address of the object. But we'd like to be more abstract than that. So a reference allows us to make that pointer opaque and hide it behind perhaps some greater sophistication. Okay? So like I say, the reference is opaque. Programs can't directly access or manipulate the pointer value anymore. And the type of the reference also is constrained. So I can perhaps cast it up a hierarchy. If I want to cast it down a hierarchy, I have a runtime check to make sure that it's actually a valid cast to do. I can't cast it into an int or a char star or anything crazy like that. And that way the runtime system has a lot more power because it can make greater assumptions about what's going to happen with these reference values. So this is a very, very powerful thing. And you'll notice here that I say that we can even do things like coalescing if we have a reference type, because the reference doesn't have to hold the actual address. The reference could hold the location of the actual object's address. So now we have two steps we take to get to the object, which sounds expensive, but guess what? Now, since nobody's holding the actual object address, we can move them around in memory. We can coalesce space and maximize the chunk of free space that we have to allocate new objects. So we can completely eliminate the possibility of fragmentation by having this reference type. So it's really, there's a lot of power that you get from this. And so I want to point out, we've already seen this concept numerous times in this class, but indirection is basically what we're talking about here. We're introducing another level of indirection between the program that we write and the actual things that it's accessing. Like you see here, the ability to reference something using a name or other value that represents the actual value. And we've seen this in our branching, so that we could actually have subroutines and return to the caller, labels as jump targets, so I don't know exactly where my loop starts yet, but I'm going to go ahead and start generating code, and when I figure it out later, I will insert the address. Pointers to access values, indirect memory access, so that we can work with arrays that exist wherever we want in memory, jump tables, and so forth. There's a whole bunch of things that are enabled by this concept of indirection. And references are just another example of this. There's this really great saying, all problems in computer science could be solved by another level of indirection. It was coined by this guy, David Wheeler, who his claim to fame is that he actually invented subroutines. You know, when computer science was young and computers were young, that kind of stuff had to be invented. I would love to have a business card where I said, yeah, I invented subroutines. Bow before me, whatever. But anyway, very, very powerful concept. Now, what do we actually use for garbage collection? Very simple approach that is used widely. In fact, you'll get to explore this in assignment 4, where you implement a very simple garbage collection algorithm called mark and sweep. You have a flag associated with every object that basically says, am I reachable? And obviously this is not exposed in the programming language to the user, but the runtime has to keep track of this, so it has a flag associated with each object. And all of the objects start out being unreachable, because we don't know what's actually reachable yet. Okay. And so we have two phases, which I bet you can't guess what they're called, mark and sweep. But we start out going through the entire object graph, the entire reachability graph, determining what it is, marking anything that we can reach from our roots. And then the second phase is to go through all of these objects that are unreachable and release them. Okay? So these are the two phases. That's why it's called mark and sweep. Okay, so we start marking the root nodes as reachable. And like I say here, we wouldn't do this in a breadth first traversal in general, because that just takes up too much space. So we can do this depth first. That's what you'll do on assignment 4. So we start with the root nodes. They're all reachable. We mark the things that can be reached from them. When we just continue this process until everything that we can reach, we have reached, and we've set it to be reachable. Okay? So now we know exactly what is not reachable. We have this little cluster of objects here. Even though there's a cycle, we don't care. We are still able to identify that that chunk of, or that collection of objects is unreachable. And so then what we do is we just iterate through all of our objects. So you can see here there's an implication that the runtime knows every single object that has been allocated. And so it has to go through all of them, because it has to obviously go through and mark that the reachable objects are now, you know, their reachable flag is 0, so that it can be ready for the next mark and sweep process. But so it can go through, mark reachable objects as 0, and then anything that was already 0 when it reached it, it can just delete. And so that's all it does. It just makes a single pass over all the objects. Okay? Any questions? This is a really straightforward algorithm for implementing garbage collection. So we end up with this. Now I say here that there are several drawbacks. The biggest one is actually that if we're going to do this successfully, nobody is allowed to change anything about objects while we're doing it. So garbage collection, while it's running, nobody else is allowed to do anything. That's why when I was using that text editor as a youth, it would pause, and I couldn't do anything while it was running garbage collection. So like I say, even on a multi-core system where you can actually do things at, multiple things at the same time, I'm not allowed to do this concurrently. So we call this stop the world garbage collection, because everything is stopped while we actually go through and collect all the garbage. And so if you have an application where you'd like to have some kind of real-time or soft real-time response guarantees, doesn't really work out very well. We can't really, we can't deal with having these pauses like this. And so you see from this that there's actually a variety of characteristics you can look at. Stop the world GC versus concurrent garbage collection, where we're able to run at least part of the garbage collection process while the application itself is still running. Okay, like you see here, the stop the world garbage collector suspends the program. Concurrent GC is able to run mostly in the background. There may still be at some point in the GC process where you have to stop everybody and do some work, just to make sure nobody interferes with it. But once you have concurrent GC, you're able to make that phase really, really tiny so that it pauses the program for as small a time as possible. So that's stop the world versus concurrent. You can also have serial versus parallel GC. Serial garbage collection is basically only allowed to use one thread of execution to do garbage collection. So you can't parallelize the process of identifying the reachability graph or cleaning up objects or anything like that. Parallel garbage collection, you can go through and assign multiple processors or multiple threads to do different parts of the garbage collection concurrently. You can imagine, for example, if you have your array of objects to traverse, and the reached objects, you need to reset their flag, and the unreached objects you need to release, you can divide that into chunks and allow different threads to traverse different chunks of those objects and do the work. Okay? Obviously, the reachability graph, traversing it would be very nice to parallelize as well. Okay? So serial GC is going to be slower, though. And then we have compacting versus non-compacting garbage collection, which is probably one of the most important parts. Because non-compacting is really where we have issues with fragmentation. Remember I talked about fragmentation? If you have a series of allocations and deallocations where the sizes of the various allocations vary, so you have some large allocations and some small allocations, and then they're released at various times, and then you have more allocations, deallocations, you can end up with memory fragmentation. Non-compacting collectors basically have a massive issue with fragmentation. So we don't like non-compacting collectors. And so this is actually the C and C++ garbage collector that you can use. It's not compacting because it can't be. And so you can have these really big issues with fragmentation. Compacting collectors, though, they're able to take the live objects and move them around, especially because we have this opaque indirect reference mechanism. And so we can use that and slide the actual objects around in memory. So we can actually take all the little bits of free space and push them all together, push all the objects together, and that allows us to avoid fragmentation. Now, one thing, I hesitate to ask this because it's going to make me probably really depressed, but who has used Windows before, like, what should I ask? XP, before XP. Okay, that's kind of nice. Who's programmed on Windows before XP? Okay, nobody? A few people, maybe? Kind of? So what about Mac OS before OS 10? That's, oh, okay, so 1. Wow, that's kind of impressive. So, interesting thing about these operating systems. What is the longest piece of software that runs on your computer? Well, the operating system starts when you boot the computer. You start various other programs, and then the OS is still running. At the end, when you shut down your computer, the last piece of software to run is your OS. Turns off the lights. Okay? So the operating system has to be really careful to avoid fragmentation. Like, so much effort is given to making the operating system able to avoid fragmentation. And one of the interesting things that you'll notice, if you do systems programming on some of these older systems, or if you ever are curious and look into the documentation for these things, a lot of these older systems will hand out handles to things. I want to allocate a window. Here's a handle to it. I want to allocate a sound sample that I can play on a device. Here's a handle to it. The reason why OSs, or I should say one reason why the OSs would hand out handles to these things is because the handle's not a pointer. And if I need to compact the memory areas used by the operating system, well, if programs just have handles to reference these things, I'm allowed to compact them. So you can see that even OSs would take special care to avoid fragmentation issues by enabling compaction in some way or another. Very, very important issue to deal with. Okay, let's see. In what situations is mark and sweep garbage collection the least expensive? We can think about compacting mark and sweep. We can think about non-compacting mark and sweep. I want to point out here that traversing the reachability graph is not really a factor in this thought experiment that we're doing right now. Because no matter what kind of garbage collection process you have to do some kind of reachability graph traversal. Okay? So in what situations is mark and sweep garbage collection the least expensive? Imagine if I have 1 million objects in my program. That'd be a lot of objects. But let's say I have 1 million objects and 900,000 of them are now unreachable. Well, mark and sweep is going to go through there. It's going to identify that, oh, look, 900,000 objects are not reachable. What does it now have to do? Yeah, it has to free each one of these 900,000 objects individually. And remember, we talked about the overhead of allocation and deallocation because we've got all this bookkeeping stuff we have to manage. I have to coalesce space. I have to keep track of if I want to have size classes for a segregated fits allocator or something like that. There's a lot of overhead in allocation and deallocation. And so if I have a lot of objects to release, that's going to be slow. Now, what if I have 1 million objects and 50 of them are now unreachable? See, that's going to be much faster. So you can see that mark and sweep really prefers situations where most objects live. That's what makes mark and sweep happy. Like I say, the mark phase always touches all objects. At least you can think of it that way. That's not an entirely correct statement there. I should probably update that a little bit. You see, I kind of ran out of space on the slide anyway. But the sweep phase is really what we're talking about here. Sweeping will take more time if I have to release more objects. It'll take less time if I have to release just a few objects. Okay, so yeah, I was talking about this. So yeah, mark and sweep prefers long-living objects. So guess what? There's another way that we can do this. It's called copying garbage collection. And basically what we do is we have multiple regions of memory in which we can allocate objects. And instead of going through the region of memory and looking for what is not reachable and then deleting each individual object that's not reachable, what we do instead is we copy the objects that live somewhere else. So you'll notice here that the term is evacuating the object. I told you that garbage collection is full of very sort of vibrant terms. You'll notice I haven't seen very many examples of computer science topics where there's so many interesting terms. Okay? But we evacuate live objects to another region of memory. And then I have this whole region of memory that is now no longer needed. It has dead objects, and it has live objects that have been copied out. So I can just wipe that entire thing in one shot. Okay? So I'm sort of batching up the delete side of things. Here's some examples. So yeah, we have two regions, from space and to space. We allocate objects in the to space. Okay, so the to space, we say, okay, I need an object, I need an object, I need an object. It fills up. At some point, it runs out of space. And so the to space becomes a from space, and we start copying objects out of it. Okay. And once we've traversed all of our reachable objects, we switch the to and the from space, so they just switch. I have pictures. I guess they're on the next slide. I'm kind of sad. I don't like having just pure text descriptions like this. And so then we resume execution with the new to space. And when it fills up, we do the same sort of stop and copy. Okay? And yeah, so it's really neat because it does this compaction automatically. It does deletion in one shot. So we don't have to do a per object delete. We just do everything in one shot. The only consequence of this is if I have multiple regions, then I can't just have a giant chunk of memory. I have to have two smaller chunks of memory. So that's not great, but that is a consequence. So from space and to space, new objects are allocated in the to space. You can see that we have various objects. They have references to each other, and so forth. And at some point it becomes full. All right? Well, I ran, another allocation request comes in. I can't handle it, so now I need to do garbage collection. So we stop the program, and we switch the to and the from. So now we're copying from the from space into the new to space. We start with all the roots, and we start copying. So I can reach that object. I can reach that object. I can't reach that third object, so I'll just copy the fourth object, and I can reach the fifth object. And the last object also is not reachable. And then that entire from space gets wiped out in one shot. Does everybody see how this? We've optimized the reclaiming process. And we've also, in the same approach, we have figured out a way to compact things automatically. So that's stop and copy. And so like I say here, stop and copy is fast when what? What does stop and copy prefer? I just said that mark and sweep loves it when most things live. Yeah, stop and copy loves when most objects die. That's what stop and copy is like super happy when everything gets reclaimed. Okay, so like I say here, not a lot of objects live through the garbage collection phase because there's less things to copy. So then I can go ahead and finish this more quickly. So this is what we start to notice. We had mark and sweep, which we really like when most things live. And then we like stop and copy when most things die. So maybe we can come up with a way of combining these two things. And I have some questions here. Do all heap allocated objects behave the same with respect to garbage collection? Or I should say, do they all behave the same with respect to how long they live? Can we find some way to take advantage of differences in behavior to create a more efficient garbage collection system? And this is where generational garbage collection comes into play. Who's heard of generational garbage collection? I would expect any sort of avid Java programmer has probably come across this term, whether you're aware of it or not. Because that happens to be what the Java virtual machine uses now, and it's relied on it for years and years. It's very, very good. In fact, in the most recent Java 8, they did some tuning to the way that the garbage collector works. They eliminate, so it talks about having these stop and copy regions, and they figured out how to eliminate one, so that frees up more space to assign to other regions. And so that was kind of a breakthrough in the most recent Java 8 release. Okay, so like I said here, most objects in a program are short-lived. Okay? I need to have an object for an intermediate variable. I need to compute something, and then I need to return a value somewhere else, and then that intermediate variable is no longer needed. I can throw it out. And so like it says here, this hypothesis or this analysis is stated as this statement, most objects die young. The other thing is that the long-lived objects don't reference the short-lived objects. Now I read this and I say, duh. Because if the long-lived objects reference the short-lived objects, then they wouldn't be short-lived objects anymore. Because they'd be reachable from the long-lived objects. So they'd probably also be long-lived objects. So you kind of have this separation between objects that live a long time and objects that don't. So these ideas together form what's called the generational hypothesis, which is the underlying ideas for generational garbage collection. And like I say, it is also known as the infant mortality hypothesis, but that's a bit rude to use as a term, so I don't use it. But here, like I say here, we have a garbage collector that takes advantage of the fact that most objects die young. We can now design a garbage collector using these different techniques, combining these techniques to create a system that is actually fast in the general case. Okay. So let's see. Now we're going to talk about. Now I say Sun in here because Sun was still a thing when I started teaching CS24. Obviously, it's not now. It's a part of Oracle, but obviously all of this still holds. And many of these virtual machines actually use generational garbage collection. We have objects as young objects and old objects. You can imagine that every object that I allocate in the system has an age associated with it. And the age is just how many garbage collection passes have I lived through. If I live through a garbage collection pass, I'm now one thing older. And then I live through another one, I'm 2 now, and I'm 3 now, and so forth. So like I say here, you have young objects kept in a separate memory area where we use stop and copy, because we expect most of these young objects are going to die. So we have Eden and 2 survivor spaces. And again, the details of this have changed over the years, but this gives you the basic idea. Okay, so the newest objects are always allocated in Eden. So again, we have various objects allocated in Eden. And then a lot of them are no longer necessary. They don't reference anything else, and they're not referenced by anything. Like the function returns, the local variables go away, those objects are no longer reachable, I can reclaim them. So what happens is the first garbage collection pass, when Eden runs out of space, we copy into one of these survivor spaces. And their age goes up. So now we know it was a young object, but now it's a slightly less young object. So it goes to the 2 space. Now what happens is the same thing as we talked about before. Objects migrate down to the 2 space until the 2 space completely fills up. At which point we switch the to and the from. We do our stop and copy thing where we have live objects that are copied from the from space into the new 2 space, and anything that dies. So we had stuff that died right away, and then we have stuff that dies a little bit later. And that stuff gets reclaimed from the from space. And I love, I have this description up here. This is what the Sun Hotspot garbage collector documentation actually describes it as. These survivor spaces basically give objects more chances to die before we decide that they're old. So we say, okay, yeah, you didn't die right away, but I still have my eye on you. You don't count as an old object yet, so you have to survive a few more garbage collection cycles before we'll actually treat you like an old object. Okay, so I talked about that. Now, like I said, these objects, they have a count with them, and as they get older and older, at some point, the virtual machine will say, all right, it looks like you aren't going to die. I guess I'm going to have to make an accommodation for you. So then it migrates that object down to the old generation. And guess what kind of garbage collection is done in the old generation? Something where we expect stuff isn't likely to die. We do our mark and sweep. That's what happens in the old generation. Okay? So yeah, the young object garbage collection, Eden and the from space are now empty. And so yeah, like I say, stop and copy, most objects die, so GC is going to be really fast. Allocating objects is fast because I just say chunk, 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 chunk. Kind of like the unacceptable allocator that we give you guys for assignment 3. We just say, here's a chunk, here's a chunk, here's a chunk. We don't do any thinking. And of course, the old generation also needs periodic garbage collection. So basically, what we do is when we really run out of space, like we say, okay, Eden is running out of space, the 2 space and from space are running out of space, the old generation is running out of space, then we go ahead and do a more expensive full garbage collection pass. And we're able to collect everything. Okay. Any questions? I think this is really awesome. This, to me, is just like a really awesome way to do garbage collection. I don't know, again, if any of you have had this experience yet in your young programming lives, but Java has this whole management API where you can connect to a running virtual machine and monitor it. And I don't know if any of you have ever connected to a running virtual machine and watched the available memory in the system. But what you'll notice is if you have a server that's running and handling requests, you'll see that memory use kind of goes up, slow, 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 slow. But it doesn't just go straight up. It's not a smooth line. What happens is it does this little sawtooth thing. It's like up and then down, and then up and then down, and then up and then down, all the way up. And what it's doing is it's reclaiming space from Eden in these survivor spaces. But stuff keeps making it down into the old generation, so it just keeps going up. And then finally, the system runs out of memory, and it says, okay, I've got to clean up all the garbage. And so then it goes to the old generation and everything, and you see a big drop. And then it does that little slow creep up again. Okay? Now, if you have a program that has a leak in it, it will just keep going up, and even those big garbage collection passes will not reclaim everything, and so you'll see sort of a up to the right trend, which is not what you want to see. But if the program is behaving correctly, you'll even notice the garbage collection of these various survivor spaces. You'll see that in the results if you plot the available memory on a virtual machine. Okay, questions? All right, yeah, so like I say, it is complicated. If you imagine, I've already talked about how objects, we have this whole notion of, okay, we have opaque references, so somewhere we have to keep track of where the actual address of the object is, and the reference refers to that indirect thing. We have to have some kind of age associated with objects. You can see now that we also have to keep track of what region of memory is this thing living in. Because I do different things with the object based on if it's in a survivor space, or it's in Eden, or it's in the old generation. I have to really keep track of a lot of details in the runtime, but I get a lot of power out of it. Okay? So like I say here, two important details. Different garbage collection algorithms work well in different situations, and program state also seems to fall into these two categories of behavior. And by combining these very different algorithms, we get a much more effective general purpose system than we would if we tried to do either one by itself. And I know because I got to use Java 1.0 where we didn't have all this cool stuff. And it sucked. It was slow. So that's another thing that I want to mention, because we'll see this idea multiple times. It's way less common than indirection. But you do notice this pretty frequently, that you have these general solutions that are constructed from merging multiple specialized solutions together. And when you have any kind of problem that can be solved in several different ways, and especially when the solutions work in different circumstances, we can oftentimes find a way of combining those things. Like I say here, we want our computers to be general purpose. We want our OSs to support a wide range of program behaviors. So a lot of times you'll see these really elegant solutions that actually combine multiple specialized solutions in some elegant way. It's true in process scheduling. It's true in this implicit allocation realm. You see it actually rather frequently, so I wanted to make sure to point it out. Okay? So if you ever have a situation where you have an algorithm that works really well in one situation but really badly in others, and you have to support those, we'll try to find a way of combining it with other solutions that work well in those situations, try to blend them in some clever way. Okay? So that's something else I want to make sure to bring out. Now the last thing to talk about, and we have just a little bit more time, and we have plenty of time to talk about this, is that reference counting is also a technique used for doing this implicit allocation. Who's used reference counting before on anything? If you happen to do any iOS programming, reference counting is a part of implicit allocation or releasing objects in your iOS app, so forth. And I think it's also common in the common language runtime that you can have managed objects that use reference counting for collection. But basically, each object keeps account of how many other things are referencing it. That's what we mean by a reference count. Okay? How many other things need me right now? And so when you have something first start to reference an object, its reference count starts out as 1. And then when anything else references, you increment the reference count again. So this reference count is always this running tally of how many other objects or pieces of memory are referring to this object. Now what happens is when a piece of the program or an object decides, I don't need this thing anymore, it decrements the reference count. Okay, so now I only have 3 things referring to me instead of 4. And at some point that reference count hits 0. And what I can do is automatically clean myself up right at that point. So like I say here, we don't have any complicated algorithms anymore. We just have a very simple process where we increment and decrement this count, and when the count hits 0, we're done. We reclaim that object. So the biggest drawback of reference counting, it's like reference counting was one of the first implicit allocation techniques that I was exposed to. And everybody sort of understands the major issue with reference counting is that if you have cycles, then you have some situations where reference counts won't hit 0 even though those objects are no longer reachable. Okay, this was the example that we had before. And every node has a reference count that basically is how many pointers are coming into that node, except for our roots, which are a special case. And you can see that we have this cycle here in the bottom right, and all of those things have a reference count of 1, even though nobody else can access them. They're not reachable. Even with this limitation, this is such a straightforward thing to implement that it is actually used quite widely. I don't know if you guys have used Python at all. Of course, you've all used Python, right? It uses reference counting internally for doing garbage collection, which is pretty cool. It actually uses reference counting for this stuff. Now, there are a couple of techniques for dealing with cycles. You'll notice that we actually have 2 places where we have cycles. One technique is to just face the fact that I'm going to have to be more clever than just relying solely on reference counts. And so what happens is you assume that these cycles don't happen very frequently, and they don't happen super frequently. But what you do is periodically you run some algorithm that goes through and looks for cycles in the reference, the reachability graph. And you try to identify those specific cycles so that you can figure out if the whole group is not reachable and then release the whole group. Okay? So this is what Python does. It does reference counting, but then it realizes that there's an issue, and so it has additional algorithms to run to identify cycles. I should say CPython, the C implementation of Python. Obviously, Jython doesn't do this. It's able to rely on the virtual machine garbage collection system. Okay? So this is one option. Another option, which is much more challenging to get right, this tends to be the one that I rely on in my C++ programs, and it is challenging to get right, is to make a distinction between strong references and weak references. So that you basically, by design, disallow cycles in your reachability graph. Okay? So you have a situation like this. If this object on the right has a back pointer to the object that references it, well, I'm going to maintain a weak pointer instead of a weak reference instead of a strong reference. And here in this cycle down in the bottom right, one of those things I have to decide, this is going to be a weak reference. Now, why do I call it a weak reference? Well, what do we know about non-weak references? We'll call them strong references. What do we know about strong references? If I reference an object, ... it will never disappear out from under me. That's what a strong reference kind of guarantees. If I have a reference to an object, that object is going to stay as long as I reference it. Weak references don't provide that guarantee. Weak references basically say, yeah, I have this reference to this thing, but it may go away, and so if I want to actually use the thing that I referenced through the weak reference, I have to test to make sure that the object that I'm referring to still actually exists. So that's what a weak reference has. It doesn't have as strong a guarantee as a strong reference. Okay, so like I say here, the weak reference doesn't increment the target object reference count, and the target may go away. And so, like I say, it properly breaks cycles, but you have to think more carefully as a programmer to use this approach. Okay? And so this is the challenge. This is why it is less commonly used. And I think we're starting to enter the realm of, well, it's kind of an implicit allocation strategy, but it's also kind of explicit because the program has to think very carefully to decide what is a strong reference and what is a weak reference. Okay? Any questions on this? Okay, so I think that's about all we're going to talk about today. So a few other drawbacks. One thing that adds up is the cost of incrementing and decrementing these reference counts all the time. You wouldn't really think about it, but if you have a local variable and you create it, you use it for a temporary calculation, and then when the function returns, the reference count goes to 0, why did I increment and decrement that in the first place? So there's actually been a lot of research about how to just assume that objects will be referenced and then release them at the appropriate time. Like if you have special cases like that, where it's just a local variable. Okay, so there's certain ways that we can actually avoid the overhead of incrementing and decrementing these things. Like I said, it is a pretty common approach because it is so simple to implement. Okay. So anyway, just to wrap everything up, you can see you get a general sense of implicit allocators now, hopefully. Like I say, it does help us to eliminate a lot of different memory management issues. So we have a simplified abstraction for programmers to now rely on. Okay, so the implicit allocator takes care of the deallocation side of things using various algorithms. And we have mark and sweep, stop and copy, and then generational garbage collection as well, which is now widely used. And sort of a corollary to this is that if we can replace pointers with something more opaque and indirect, then we can step around some of the other issues that we run into as well. Okay? Like being able to compact memory. And also disallowing things like buffer overflows and so forth. Okay? Any questions? All right, on Wednesday we will pick up the next topic. We'll see how objects work.